You're listening to AI Podcast. I'm Ethan, and today we're unpacking a paper called Self-Discover, short for Large Language Models Self-Compose Reasoning Structures. The headline is straightforward. Instead of jumping straight into step-by-step reasoning, the model first designs a small plan for how to think about a task, then follows that plan to solve it. That simple change tends to produce more accurate answers while relying on fewer repeated guesses than common sampling tricks.
So the model doesn't just think step by step. It first decides what kind of steps make sense for this task, then executes them. That's a useful distinction.
Exactly. You can think of it as task-specific metacognition. Rather than using one fixed reasoning style everywhere, the model composes a compact structure of skills that actually fits the task.
Before we go deeper, who's behind this work?
The paper is led by Zhou, with collaborators from the University of Southern California and Google DeepMind. Representative authors include Xiang and Zhou. It appeared on ARCAF in 2024 and was published at NeurIPS 2024.
Great. What problem are they trying to solve in practice?
A lot of prompting methods help with reasoning: chain of thought, least to most, plan and solve, reflective prompting. Each is like a single tool, but different tasks need different combinations of skills. Sometimes decomposition, sometimes verification, sometimes careful use of world knowledge. The gap the authors point out is that we've been missing a lightweight, training-free way for a model to first figure out which skills matter for a given task, and then stick to that plan.
So the usual approaches are helpful, but one size fits all. This paper tries to tailor the style of reasoning to the task itself.
That's exactly it, and it does so with prompting alone, not model retraining.
What have people tried already, and where do those methods fall short?
Chain of thought shows steps but assumes one mode of reasoning. Self-consistency samples many chains and votes, which can help but burns a lot of inference calls. Decomposition is great for compositional problems, less so for nuanced common sense. Plan and solve separates planning from solving, yet still uses a preset style. Prompt optimization can learn strong prompts, but usually needs training data, and the prompts aren't always interpretable or transferable across model families.
Right, we want flexibility without making everything heavier or opaque.
Here's the core idea. The method runs in two stages. First, there's a brief task-level discovery step. The model is given a library of general reasoning skills. Things like break the problem into sub-problems, think step by step, reflect and verify. With a short sequence of meta-prompts, the model selects the relevant skills, adapts them to the task, and implements a simple key-value style plan it can follow. Second, at inference time, the model uses that plan to solve each example, filling in the fields step by step. Bad.
Almost like the model writing its own playbook before it plays the game.
Exactly. And because the plan is explicit, a person can read it, see what the model intended, and debug failures more easily than with a monolithic prompt.
Where did they test this approach?
They evaluated it on a suite of challenging settings. Big bench hard for diverse reasoning, thinking for doing for grounded decision-making, and a subset of competition-style math problems. They compared against direct prompting, standard chain of thought, plan and solve, and sampling heavy baselines like self-consistency, along with a prompt optimization method. They used strong general models and also checked transfer to other families.
And results?
In short, consistent gains over chain of thought across those benchmarks, with especially notable improvements on the grounded decision-making tasks. Efficiency is part of the story, too. Because the method uses one run per example, not many samples and a vote, it cuts down the number of inference calls. Now, the plans and the reasoning traces can be longer, so total token cost depends on the setting, but in terms of repeated calls, it's leaner. A nice bonus is transfer. Plans discovered with one model can help another model, and the plans are easier to interpret than opaque optimized prompts.
That interpretability is appealing. If I can read the plan, I know where to look when performance dips.
Exactly. Their error analysis on math also suggests many misses come from execution or calculation mistakes rather than from a flawed plan. That points to clear next steps, like adding verification or lightweight tool use.
Let's talk caveats. What should listeners keep in mind?
First, reproducibility across closed models is tricky because APIs evolve over time. Second, the math evaluation used a relatively small slice of the full benchmark, which keeps costs down but limits statistical confidence. Third, the method depends on a curated library of skills and specific meta prompts, so performance could be sensitive to the exact phrasing and module set. Finally, while it reduces repeated calls, longer prompts and outputs can raise token usage, so full cost depends on both calls and tokens.
That's a balanced picture. How does this differ from other planning style methods?
Plan and Solve adds a general planning phase, but it usually prescribes a single planning style. Self-Discover composes a plan from multiple small skills that can vary by task. It's closer to handing the model a toolkit and asking it to build the blueprint it needs.
If I wanted to try this at work, where would I start?
Start by writing a clear, plain language library of reasoning skills. Then use 3 short prompts to have the model select relevant skills, adapt them to your task, and implement a compact plan it can follow consistently. Pilot on a small set, read the plans, and refine your skill library or wording. The readability makes that loop practical.
And I shouldn't expect one plan to win everywhere.
Right? Different tasks invite different compositions, which is the whole point.
Where do the authors think this should go next?
Standardize and share skill libraries and discovery prompts for easier replication. Automate the growth of the skill library by mining good skills from past runs. Add cost-aware control so the plan length adapts to a budget. Evaluate on broader, newer benchmarks, including tougher programming and symbolic reasoning, and pair plans with verification or simple tools to reduce execution errors, especially in math-heavy settings.
All right, give me the crisp takeaway to close.
Let your model decide how to think before it starts thinking. Composing a small, task-specific plan can deliver steady accuracy gains with fewer repeated guesses, and it leaves a transparent artifact you can audit and transfer across models.
Clear and helpful. Thanks, Ethan, and thanks to everyone listening. This has been AI Podcast. See you next time.